Hello, good evening and welcome to tonight's Audio Engineering Society UK section webinar. How on earth did we electronically vary the amplitude of an audio signal before digital signal processing? In tonight's talk, Professor Jamie Angus-Whiteoak from Salford University will gently introduce us to voltage-controlled amplifiers, or VCA for short. Starting with a quick look at the VCA family tree, she will explain how each works and discuss the limitations, how these limitations interacted with the design of circuits that use them, and show examples of each one in use. From an early age, Jamie has spent much of her free time studying audio, radio, synthesizers and loudspeakers, and even managed to build some. She is the author of many audio-related patents and has worked on signal processing, analog circuits, diffusers, and numerous other audio technology topics. Jamie has been active in the AES for 33 years and is currently VP for the Northern Europe region. Amongst many awards, Jamie has recently received the AES Gold Medal Award for extraordinary contributions as an innovator and inventor in the fields of audio science, acoustics, and signal processing. Jamie's talk will begin in a moment and will take us up towards 8 o'clock. She's happy to answer any questions you have, so feel free to use the Q&A button at the bottom of the screen. So that's enough for me. Now it's time to hand the stage over to Jamie.
Hello, everyone. Nice to be talking to you all. So what I want to do today is to talk about analog voltage controlled attenuators and amplifiers. The two are sort of interchanged. So yes, how did we vary the amplitude before DSP? Well, Neil's covered some of that. In the digital domain, varying the amplitude of an audio signal is simple. You multiply the sample value by a coefficient like 0.5, 0.01, 0.007. There might be some issues with zipper noise when you change things rapidly, but basically that's it. Analog, however, is a different story. We actually need to change the value of an analog circuit. Usually the circuit is non-linear that does this, and there have been many creative approaches to how we do it. So what I want to do in this talk is have a quick look at the VCA family tree. We'll exclude a couple of approaches, we'll see why later, and then we'll go through the different main approaches, explaining reasonably simply how each method works and discuss their limitations and problems. And if I can, show an example of each one. We won't be doing any audio examples, but just how the different circuit topologies are used within the circuits. So without ado, let's look at the VCA family tree. As you can see, we've got a series of different options. Two I'm going to exclude, and that's all the discrete switches or FETs mostly, and multiplying digital to analog converters. I'm also going to ignore motorized pots because, to the best of my knowledge, we don't have any signal processing we use in the studio. But I'm going to look at the other ones, and they essentially go into two types, what we might call voltage-controlled resistors, which are things based on a lamp coupled with a light-dependent resistor, and something called a field effect transistor. And we'll also look at voltage-controlled amplifiers, which include variable transconductance type amplifiers and log-anti-log amplifiers. And finally, very briefly, we'll touch on pulse width modulation switches, as there are some products that use those. So let's have a look at the first one, light-dependent resistors. What is a light-dependent resistor? Well, very simply, it's usually something based on cadmium sulfide, although there are other materials, put on a substrate, and it forms a light-sensitive resistor. When you shine a light on it, the resistance drops, and how much it goes down to depends on both the geometry of the light-dependent resistor and to a certain extent its width and doping. And these devices can have very high dark resistances on the order of a megaohm. Now, resistance isn't perfectly linear with illumination, although some are quite linear, but there's a typical example off to the side in the drawing next to the text. The response time is also not linear. It's actually dependent on illumination, and it's faster for bright lights. It can go to low resistance very quickly. It's slower for weaker lights, and also it depends on the history of the illumination, which we'll come back to later on. And long periods of bright light actually make the decay response it takes to get to higher resistance. Here's a typical date for a light-dependent resistance. Thing I want is that for high illumination, 1,000 lux, is actually quite a low resistance on the order of 400 ohms. For something 100 times less, it goes to about 9 kilo ohms. But if you put no light on it at all, it ends up with a resistance of on the order of a megaohm or even higher. So sort of in the rise and fall times, it can respond to low light very quickly. Response to the absence of light is 10 plus times to 100 times slower. And actually to get to the full dark resistance, it's very slow indeed. There's also not mentioned on this, there's huge inter-device variation. Having 30% or that sort of variation between different devices from the same batch is not unusual. So it has some issues there in practical devices. Now, if we're going to use a null light-dependent resistor, we're going to have some source of light. Incandescent bulbs, basically too slow and variable. Neon and variable, so neither of those are usable. In 1958, when these things first came out, LEDs were not, so 1968 was the first practical red LED. So what they used was essentially a high voltage electroluminescent panel, which was a very effective light source and responded reasonably quickly. Interestingly, the light was proportional to the AC level of the signal. So you didn't have to rectify or do any extra level detection. Essentially, an electroluminescent panel, brightness depends on the level of the signal going into it, even if it's an AC signal. And they were coupled together, and these devices were actually made. I've got a few pictures here. They were in an octal package, which meant they were compatible with the valve bases of the day. And you would have two light-dependent resistors, and then you can see just above it there, that's the electroluminescent package, and they could all be placed in a convenient light-sealed module. Usually were two matched L light-dependent resistors, because they would use one to drive the metering that you would need in a practical device. Now, let's look at the timing of this, because I think this is quite important. The combination of the two modules had a very fast attack. You can see there from a high resistance here, it's sort of on the order of 10 megohms. The minute you apply light, it's down to about a kilo ohm in probably under 10 milliseconds. Note the time base here is in seconds, not in milliseconds. And then when you stopped the light, there would be a rapid recovery over about to about 100K, and then a much slower recovery to around a megaohm, and then much slower recovery up to the 10 megaohm value. So you can see how the time varied, and the decay time would depend on the amount of compression. Now, it turns out for compressors, that's actually quite a useful characteristic, because it meant it responded quickly if the signal suddenly got loud, but in fact, in the way it responded afterwards, it responded in a, for want of a better term, a musical way. It would have a reasonably quick adjustment over about a second or so immediately after the signal got quieter, and then would gradually get to a higher resistance after that. Now, the little side thing there, because of the non-uniform, the non-linear response to light, and with the response of illumination to resistance, it affects the topology you could use in a compressor. It turns out there's actually two different basic approaches to compressor limiter technologies. One is the feedback topology, and that's where you derive the control signal from the output of the gain control stage. So if for want of a better term, the detector sees the effect of the gain control device. Now that's really helpful, because if you've got nonlinear gain versus control voltage characteristics, it's easy to accommodate them. Essentially, the device adapts to that. For feed forward, the control signals derived from the input of the gain control stage, and therefore the relationship between control voltage and gain reduction must be very precise. It can be a problem with something like a light ender, so they tend to be used in a feedback configuration. Of course, feedback configuration always has a certain level of delay in responding to a sudden change in signal, which a feed forward device can overcome. And very importantly, because in one device, the gain control is within the loop, so to speak, and the other one, it's not. The actual dynamics of the two devices, even using a similar gain control device, will behave differently. Feedback compressors tend to have a softer limiting response than feed forward. You don't get such sharp knees on it. So let's look at LDR, light dependent resistor compressor. Classic piece of gear, the LA2A compressor, created in 1962. It's a feedback compressor, even though it looks as if it might be a feed forward, because everything's happening at the front of the system. When you look at it in detail, you'll find that the actual signal that gets fed to the amplifier is a function of the gain, the light dependent resistor. So it's actually a feedback resistor. In fact, many of these devices actually do put the light dependent resistor right at this is the electroluminescent panel there. So the panel's light output was proportional to the AC signal. Very usefully, the control signal is isolated from the audio path, so you have no worries about getting control signals into your audio, and certainly for the time, less components required because no signal rectification was required. Of course, that meant you didn't have any control over the time response to the signal. It was all done by the natural time constants of the light-dependent resistor and the electroluminescent panel in combination. The compression amount was essentially set by the gain of the drive amp. The higher the gain of the drive amp, the more compression you got, and the attack release times were set by the light dependent response. So it's actually possible, if one goes a bit further, it's possible to make the control all linear and allow feed forward compression by using two matched light dependent resistors and some simple circuitry. There's an example there shown on the right hand side of the screen. The challenge for these are you need two matched light dependent resistors, so it does require some selection to make that happen. And if you're using an LED, you'll actually need some level detection circuitry to drive the LED. But it's certainly possible, and it did make me think that you could consider doing a modernized version of an LA2A type thing, using two matched LDRs and some simple circuitry, but actually using AC LEDs, for example, that like we use in lighting. The example I've shown there is a 12-volt one, and maybe get something that will behave very similarly. That's just a thought for modern circuitry. There are modern devices out on the market using LED and signal detection circuitry to achieve the same effect. Okay, the next form of voltage controlled resistor is the field effect transistor. And how these work is that at low voltages, less than the pinch-off voltage of the field effect transistor, this so-called ohmic region, the field effect transistor actually acts like a voltage controlled resistor. And this resistance will vary with gate voltage relative to the source of the field effect transistor. And a low gate resistance means a low resistance in the FET, and a high voltage means a high resistance. Obviously, by varying the voltage, you can vary the resistance fairly readily and fairly easily, and it works surprisingly well. However, there are a few wrinkles. One is obviously the resistance can vary. So here we can see VGS equals -3 volts. It's quite a high resistance. At 0 volts, it's really rather a low resistance, but you'll notice they're not straight lines. In fact, they're rather bent. And that means that they're non-linear if you go too much outside the voltage range, about above a few fractions of a volt. And that's a problem. But there is a way you can improve it. Sorry, just before I get into that, the actual resistance isn't a linear variation with gate voltage either. As you can see here, it's quite a rapid change as you're close to the cutoff voltage. A very small change in control voltage results in a rapid change in resistance, whereas close to 0 volts, quite a large change in voltage, control voltage actually doesn't change resistance by that much. I would suggest that really from about 0.8 of the cutoff voltage to 0 is something that's practical to do. Although in theory you can get 60 dB voltage change, actually trying to do any control in this region is very difficult. And because it's a nonlinear function of control voltage, again, you tend to find these devices used in feedback configurations with compressors. Now, the real problem is the nonlinearity. And you can see here that really it's starting to get quite bent above about 0.4 plus or minus 0.4 volts. So you're restricted to quite small AC voltages being controlled by these devices. You can improve them. And the way you improve it is by deliberately adding some of the signal voltage to the control voltage, which you can either do very simply with a voltage divider here, which works fine, but it means you need twice the control voltage to achieve the same effect. Or you can actually add the necessary audio signal to the control voltage using a voltage divider, or adding to the control voltage, which doesn't increase the control voltage required. The effect of this is actually dramatic, which you can see here. You can see now that we've probably doubled the usable signal value. So we've got a 6 dBs increase in signal voltage, even more so at very low control voltages. And this considerably improves the dynamic range. So what can we do with these things? Well, here's, we can use them in conjunction as one leg of a simple passive attenuator, as shown here. And this just acts like a normal voltage divider, except the lower resistance is controllable by the control voltage. If we need more gain reduction than you can do in one stage, then it's always possible to cascade two together and double it up to give a greater range. The only thing really that we notice is that the control law isn't linear. Now here's an example of it being used in a compressor circuit. Again, another classic piece of gear, the UREI 1176. This may look like I'm having a gear fetish here, but honestly, I'm not. I'm just having a gear circuit fetish. So here's, now this is quite an interesting circuit. Here's the field effect transistor that's doing the attenuation and the control. This is just amplifying things up. Now the distortion, however, and the control is fed in here from the detector as a DC voltage, but very interestingly, notice we have 22 megs and 2.2 megs and 2.2 megs here. It's actually using the output of the amplifier after the FET to feed half a control a signal into the field effect transistor to adjust the to reduce the distortion. And of course, because it's a field effect transistor needs a voltage, we actually need a separate signal level detector, which is extra hardware, but also gives the opportunity of adjusting the attack and decay and the other things we might want to do with control of a compressor. And just to show there, that shows the feedback path to reduce the distortion as well as the control input. And here's another one, which is rather interesting. This is the Dolby, this is the CAT22 card compressor system. And again, it uses it actually uses two field effect transistors to control the gain, to control the amplitude. Again, needs a separate level detector, and it also takes a signal, the output of the amplifier there, and adds it to the control signal, which is coming from a detector circuit off screen to reduce the distortion. And again, the Dolby compressor is also a feedback compressor because of the nonlinear control or field effect transistors. You're pretty much committed to using a feedback style compressor to make them usefully work over a range of component values. In fact, these FETs had to be matched quite carefully. We also use a voltage controlled resistor to control the frequency of a filter. We can use it as a low pass filter if we want to. That's a little bit tricky to actually instrument, or as a high pass filter, which is a little bit easier, but they can create a voltage controlled filter, again, with a nonlinear control law. And I've got a little application here, another famous bit of gear, the phaser circuit from Eventide, if I think I remember that correctly. And it used, this is an all pass filter here, and you can see it's using, if you like, the FET as a voltage controllable high pass filter. Again, we're actually using half the drain voltage to reduce the distortion due to that. And you'll notice it's actually using a metal oxide semiconductor field effect transistor, a MOSFET. And there are actually 8 of these sections cascaded to get enough phase shift to have a decent effect and sweep range. Because they've used capacitors, they don't have to worry about having twice the control voltage because the capacitors block the DC. But that's another application of using a field effect transistor as a voltage controlled filter. Right. Now we come to the other main class of devices, which is to look at varying the operating point of a device. And if we look at something like a semiconductor diode, there's actually an exponential relationship between applied voltage and current. And you can see here the current versus the volts is very dramatic over a very small voltage range. And that's a bit of a problem. If you look at it in terms of the diode current versus the input voltage on a log scale, they're actually very closely matched to a logarithmic curve, exponential curve, and that gives some good aspects in that they're quite well defined. Unfortunately, the actual dynamic resistance is very temperature dependent. It's linearly proportional to the diode current, approximately 26 ohms divided by ID, or exponentially proportional to diode voltage, which allows you a dB proportional control voltage if you want one. However, we can use this to vary the gain or attenuation of a circuit, but 2 big issues. One is obviously you're using the control current or the control voltage is immediately visible to the output. So control voltage feed through is an issue. And unless you make the signal very, very small, you actually get quite a high level of distortion from there. You can see here, you're looking at tens of millivolts really to have low distortion. You can still use them, and this is the simplest sort of circuit one can think of. I wouldn't recommend it, but we can have our audio input coming in here, which going through a resistor. We can have a resistor here, probably quite a high, much greater than R1, which converts the control voltage into a current, and depending on the control voltage, altering the current through this diode, which changes the resistance, dynamic resistance of this diode, so you can get a varying attenuation for a small input signal. And that's very simple. It can work quite well. Unfortunately, the control voltage appears on the output, so you get thumps and things due to the change in control voltage. The signal voltage itself will also dynamically modulate this impedance and therefore cause distortion. So you need small signals to avoid harmonic distortion. Now, how might we go about solving that? Well, one way to do it is to actually use more than one diode in a bridge arrangement, feed it with a symmetrical signal, and sense what comes out of that balanced signal with a differential amplifier. 2 things happen. One is that the DC voltage varies in a common mode way, so it's cancelled out by this arrangement here. But the other interesting thing that happens is if you have an AC signal, if it goes, as it moves up and down, it will essentially modulate the diode resistance above it such that it becomes higher, and the one below, it'll become a little bit lower. So these 2 cancel each other out to a certain extent. and therefore it reduces the distortion. But it is to work, the diode matching has to be absolutely critical, and you still end up using really quite small signals to avoid harmonic distortion. This arrangement was used in 1960 compressor designs. I don't have an example of one, but also is used a lot in synthesizer circuits, both for for envelope control and also for filter control in synthesizers. So in those particular cases, I think possibly the distortion was less of an issue because it was, if you like, part of the character of the instrument itself. So, and however, again, here's an example of a diode compressor type circuit used in anger. This is the Dolby A301, which is the first ever Dolby A noise reduction system. And I find it actually quite fascinating that you can use different technologies to achieve the same goal. So this is the same system that used FETs when the later versions came out. But here we have them using a diode compressor, actually two series diodes, a germanium and a silicon one. I think that was to try and get a softer turn on characteristic and lower distortion. But essentially the control input here varies the current through both these diodes, and the input signal is again fed to a resistor there. This forms the attenuator leg, and likewise this one forms another attenuator. And like the two halves of the bridge rectifier, the signal distortion cancels itself out, and then these two signals are combined through here to cancel out some of the distortion caused by the system. And it also helps reduce DC component feed through, but you still need quite small signals. So what can we do instead of that? Well, this actually came before the Dolby system and 60s synthesizers, and that was to use a tube or a valve's mu or transconduction variation with operating point. Normal tubes and valves use constant pitch grids, and that gives you what's known as a sharp cutoff characteristic. And what we're seeing here is the transconductance and the anode current vary as the operating point varies. And you can see you can vary over quite a wide range. If you use an elliptical Helios where you've got narrow spacing and wide spacing, what happens is it takes much greater negative voltages to turn the valve or tube off. And that's called a remote cutoff device. Again, you can see there the relationship between the transconductance and the control voltage is still can go over quite a wide range. And in both types, the transconductance and gain vary as you vary the control grid voltage and effectively the anode current. The main reason for using remote cutoff devices is that because it's so much higher, you can get away with a much larger AC signal for the same amount of distortion if you're varying the gain. Here's an example of a remote cutoff tube or valve. I'm using this particular one because it's used in the next example. It's got variable spaced grids. You can see here that the transconductance varies. It takes quite a lot of voltage to get it down to a low transconductance. But the real thing we want to look at is something called the mu, and it's a bit hard to see it on this scale. So I've expanded it up. It's a little bit, sorry about this distortion, but the amplification factor or mu here varies from about 8 if you have a anode voltage of 100 to on the order of, what's that, 40. So it varies from about 8 to 40, which is about an 18 dB range of gain. And you have to use, again, you have to use these in balanced circuits to avoid control voltage feed through and thumps, but also it helps you reduce the distortion that occurs due to this, the variation in gain caused by the signal. And the nonlinear variation with voltage pretty much mandates the use of a feedback compressor. And here's again another classic variable mu compressor. I've chosen it only because it's the simplest one I could find. The variable mu triode here, double triode, is the amplitude control device, and the control voltage comes from here and varies the bias on the triodes, and therefore varies the current through the device and therefore the gain through the device. You do need a separate signal detector, which is achieved here. This is essentially two diodes doing full wave rectification of the signal from the output of the compressor, which is again off to the right of the screen. You'll notice that having the separate rectifier allows you to control both the attack of the device and the release of the device, of the voltage stored on the this, if you like, time constant capacitor. So again, fairly simple circuit, but nevertheless quite a powerful one. Right. The final way we can vary the transconductance is to use the bipolar transistor. We know this semiconductor diode has an exponential relationship between the applied base emitter and, transistor has an exponential relationship between applied base emitter voltage and corrector current. Again, it's unfortunately highly device and temperature dependent. The GM is linearly proportional to the current, the transconductance, and it's logarithmically proportional to the base emitter voltage. So again, has some useful characteristics, and we can directly use this to vary the gain or attenuation of a circuit. And again, the control voltage feed through is an issue, which we need to deal with, and distortion is high unless the signal is very small. One way of doing it is to use something called an operational transconductance amplifier, and essentially the control voltage coming in here varies the current through these two transistors, which varies the transconductance. Because they're balanced, the effect of the control voltage is cancelled out, and then needs to be amplified up. Unfortunately, this whole circuit has to be operated in an open loop mode, and the distortion is actually quite poor, even with linearizing diodes. These devices here were there to try and make it a little bit more linear. It was used in synths and pedals quite a lot, but you can see without using the diode, if you get more than 30 odd millivolts coming to it, you've got 2% distortion. You can get that up to a whole 100 millivolts if you use the linearization diodes, but this is not something you could call high fidelity or a good quality. So, but useful nevertheless. There you can do a little bit better. There is some play around with balancing things even more. And there was a chip produced called an SSM 2014, which actually managed to do it with reasonably low distortion over quite a wide range, and control voltages were via the transistor bases, which let you have a dB versus volt per volt control. And matched transistors removed most of the temperature variation, and clever cross-coupling cancellation technique gave you low distortion over a wide range of gains for reasonable signal levels. Produced quite good results. The other way of doing it is to use logarithms. And we all know if we add two logarithms together, we're multiplying things together. So if we can create the logarithm, in principle, we can add the log of the control voltage to the log of the audio voltage and control the gain that way. Of course, it's a little bit of a problem because it's highly temperature dependent. The whole thing is a exponential function of temperature, and logs don't actually handle negative values. Log of 0 is minus infinity. So ignoring those minor practical problems, in principle, we could do it if we could solve the temperature issue and handling negative values. So how do we stabilize it thermally? Well, the answer is we use two transistors, one as a reference to the other, and ideally these sit on the same piece of silicon and are intimately coupled, so they're essentially at the same channel temperature. If we do that, we can actually cancel out any thermal issues, but we still can't handle negative voltages and log of 0. We can create the antilog to get things back, but we still can't handle the negative values. And we can combine the log and antilog circuit together, which gives us this wonderful complicated circuit here with 4 transistors. It multiplies and divides, but it's still unipolar. It still can only handle positive signals. We'd also really like a control of dBs per volt. That's very convenient for a lot of audio uses. So exponential control. So I'm going to move from this complicated circuit to a much simpler circuit that actually does that. So the first thing to do to recognize is that if we take out this section here, E3, which is a multiplier, and apply the control signal to the base of this transistor, we can get an exponential control of the gain of that circuit. Still only unipolar. If we then look at that, we'll notice that actually this circuit's now redundant, and if we combine this circuit with this circuit, what we get is a much simpler circuit where we've got plus and minus dBs per volt control signals and a multiplier circuit that pretty much does what we want it to do and can do it over a very wide range, except that it still can't handle a bipolar signal. It's still only positive signals. So how do we get an AC signal out of that? Well, there's a couple of different ways. The first one done by Valley was to add some extra bias diodes into the circuit. Really no other change in that. And you find that gives you class A bias. So there's you can actually have AC signals going through this now. And have a log multiplier that goes over a very wide range. And this circuit actually had very good performance indeed. The only problem with it is that because there's a lot of current flowing through the transistors, is it did have an issue with noise. So we finally got to the David Blackmer's bipolar log anti-log, which actually used 2 sets of transistors, a PNP and an NPN type transistor, PNP, NPN, and allowed you to bias it. And that gave you exponential gain control, which allowed you for feed forward and feedback compressors and expanders, handled bipolar signals, and you could adjust the bias on it to have class A or class AB, or even dynamic biasing to try and optimize distortion versus noise. And again, that was used as part of a product, the DBX noise reduction circuit, but it's also used in compressors and other devices as well, and had a very high dynamic range. 100 dB was not an unreasonable range to expect. So actually quite a good performing circuit. Right, there's one other one which I'm going to briefly talk about, and that's pulse width modulation. We can actually use the switch, analog switch, to vary how much the audio signal is let through the device. You then have to filter it. It was done by people like Dave Hill from Hillsong, and you can do it either with a series switch, which I haven't shown, or a parallel switch. And essentially you can have a linear with a linear controller on. It's a very consistent controller, and you can also make it with a log controller if you want to. You use very high frequency switching frequency, typically on the order of hundreds of kilohertz outside the audio band, so you can then filter out the high frequency signal. And this is just an example compressor that used it, used pulse width modulation at about 200 kilohertz for the frequency of the pulse width modulation control. And they advertise as having a 40 dB dynamic range, but really in terms of linear control, if you wanted to use it in feedback mode, it's closer to about 35 dB, which is still quite a good control gain range, although not as good as the DBX type systems. So to conclude, there's a large number of creative ways of implementing analog VCAs. Mostly they're based on non-linear characteristics of devices. Tolerance is definitely a problem with a lot of them. You need matched valves. Light-dependent things need matched light-dependent resistors. FETs needed matched FETs. Even using diodes in the Dolby thing, I didn't show the circuit, but there's stars all over that circuit that essentially says all these components have to be matched, measured before production and matched very closely. Control linearity was also a problem for some of them, but each device creates its own sound and solutions, and digital VCAs have their own issues. And that's it. Any questions?
Well, thank you very much, Jamie. That was a fascinating talk. Oops, stop my video again. Certainly covers a lot of
questions.
Yeah.
Q&A.
So let's go to the Q&A. So first question was from Elliot Senatov. I think it says in relation to the LDRs. Yes, fairly early on in your talk. Were these meant to be used for compressors, or was it accidental? I mean, were these components specifically made for compressors, or was it a general purpose component that some people found, hey, this works?
The light-dependent resistors are still in use. I mean, anything involves interrupting a light beam to control something. Light-dependent resistors are actually quite popular. They were also used for British Rail to detect hot boxes, which is bearings that are getting too hot and might cause a wheel to fall off, which is obviously quite embarrassing if you're on a train. No, I think the combination of the electroluminescent panel and the light-dependent resistors was very specifically made to make a compressor. And I think the person that invented the first one made them up to do that, because they might have been also made to control, give you some way of controlling a resistance will have to have an electrical barrier insulation barrier between the two circuits, which you might have to use in, say, petrochemicals. But the actual device I showed, I'm pretty sure was very much designed specifically for gain control devices like compressors, limiters. And actually they work quite well because although you might not think it, the actual time constant, the way the light dependent resistor behaves is nice, for want of a better term. It does something quite nice to the audio. So, there are worse things you could do.
Sure. Okay, so Conrad Cook is asking the AC30 vibrato channel, tubes and valves. What's your opinion on it? Is it any good?
I have no tubes and AC30 vibrato channel.
The AC30 is a guitar amp, and then just
yes, I know what an AC30. I have to crank it up really loud to get the distortion, which is a bit of an issue. I honestly, it will be using something like a variable mu type approach to do that if it's doing it with valves. For a guitar amp, it depends what you're wanting to do with it. I mean, I think, guitar amps are intended to distort a little bit. So the fact that it might not, I have no idea what the AC30 vibrato channel looks like, whether it's done with a single valve or a balanced system, but it's a way of doing it. It will have a characteristics, which at the end of the day is probably a matter of personal opinion of the musician using it.
Right.
Because it's not really vibrato, it's varying the amplitude rather than frequency, but
that'd be tremolo, I think, isn't it?
Yeah.
Okay, next
yes.
Next question from anonymous attendee. Why is it so hard to replicate these circuits in digital signal processing? Harmonics are different in digital compressor copies versus the original analog.
It's really hard to match them in digital circuitry because digital signals are sampled. And one of the issues you have with digital signals, and I don't know, is the talk the samples are not what they seem, or something, or the piece.
That's up on our YouTube
that's
channel.
Up on YouTube. You might want to look at that. Essentially, to make these nonlinear devices work, you need the waveform, all of it, not the sampled version of it. If you just apply rules to the samples of a nonlinear device, you're not going to get the same result as a continuous linear circuit. So, I mean, I think there's no reason in principle, but of course, in practice, it's actually quite a bit harder than simply writing the equations out on the samples. You actually do have to have something approximating a continuous form. And then there's the other aspects of the sound of these things, which are due to the imperfections of the tubes or the other devices. And, tubes don't follow the equations. They sort of follow the equations, but you have to remember things like Child-Langmuir and other bits and pieces are approximations. Remember, physicists, when you ask a physicist how to cook a chicken, how do you roast a chicken, he will say to you, or she will say to you, first assume a spherical chicken, and then they can calculate it.
Yeah.
All the valve equations we've got are actually approximations. So actually happens, it's a whole different ball game.
Great. Okay, so that's that one answered. Right, next question from Juan Sierra. You mentioned issues about tolerances in manufacturing. What about differences in aging and degradation through time? Which types are more resilient to the pass of time?
Oof. Well, valves inevitably decay over lifetime. So you're going to have an issue with that. I think even the light dependent resistance one although the LD dependent resistors, if they're well sealed, should behave fairly consistently over time, I think the electroluminescent panel may end up getting weaker as time goes on. So they, there are problems. Transistors, again, modern, something like the DBX, the Blackmer compressor system, if it's done on a good process, theoretically, so long as you don't stress it too much, stay very similar. I mean, I think there are other, when you look at stuff that's been built in the 50s and 60s, some of the passive components have issues with lifetimes, electrolytic capacitors. I know with interest, the Dolby 301 circuit actually had tantalum capacitors in, which probably seemed like a really good idea at the time, but probably is not such a good idea now because they're notorious for failing. But electrolytic capacitors go off. Old carbon resistances do degrade with time as well. So there are degradations in these things anyway. You often hear of people they say recapping a piece of old equipment. Electrolytics seem to be the first to go, but you'd probably have to change the tubes or valves periodically as well, which is also a problem because some of them are not made anymore and are not available if you've got money. That dual triode, I don't think that's actually available. That's the one that I showed in the variable mu thing. So next.
Yes, next question comes from Paul Colvin. He's surprised you didn't cover work after Blackmer by people like Dave Baskind and Harvey Rubens.
Well, I tend to allow a certain amount of time per slide. So yes, there are some more modern ones, but again, I was trying to show the basic principles. I'm not particularly sure about those particular names, or whether I can get the circuits. I mean, that's the other thing when you're doing this. You try and use devices where you can actually find some circuits to talk about. But I think it was an hour's talk with what I had, so I think I probably exhausted everybody's patience anyway. But yes, I mean, people are continuously improving them. I mean, I didn't cover any of the newer optical compressors based using LEDs and light dependent resistors, of which there are quite a few out there. So, these are always old kit thing. There are new variations and being made, or that have been made in, the last 20 years or so. So certainly that's a very good point. I can just encourage people to have a look at it. I think they would tend to fall into one of those classifications, though.
Yeah.
So
yeah, and sort of follow on from that from Alex's case was the present day VCAs by, you either pronounce it as that or THAT Corp.
THAT.
Yeah. From the original Blackmer.
Now I'm just I haven't looked at their most recent ones. I thought at one point they were using the SSM 2016 type topology in terms of that. So it's a transconductance based voltage controlled amplifier, but I'm willing to be told I'm wrong on that. So I mean, as I say, in terms of semiconductors, it seems to me there are two major branches. One is varying the transconductance explicitly, and the other one is doing the log-anti-log type approach. They have pros and cons, and they seem to achieve not dissimilar performances. Who was it? I can't remember his name. Studio Sound in the late 80s, early 90s, did a series, Ben Duncan did a
Yeah.
series there where he measured a bunch of them. And what I found very interesting was that the DBX and the SSM parts and the Valley parts, all, when you looked at them, they were all achieving dramatically better dynamic ranges and control gain ranges, but they also all, it was more a balance. They weren't necessarily just, and they were all in the ballpark. There wasn't anything that was light years ahead of everything else. You were either, the Valley ones were better in terms of distortion, but weren't as good in terms of signal to noise ratio. Whereas I think Blackmer Class B, higher in distortion, but better in signal to noise ratio. And in terms, when we're talking distortion, we're talking 0.0 something percent, not 1% or anything like that. So, yeah.
Okay.
So,
Cool. Next question from Andy Turadich. Surprising that mini CRT was not used as an illuminator with LDR.
mini CRT.
So maybe a small screen.
Probably because, yeah, I mean, I think, all right, this is completely off the top of my head, but it would be it's a lot cheaper to have an electrophosphorescent display, which is a thin wafer, compared to a little cathode ray tube that you're going to have to scan and modulate the beam on. That's probably more expensive as well in terms of a device. So they tended to have two light dependent resistors, one for the metering and one for the actual gain control. You could put them in a feedback path and use the metering at light dependent resistor to linearize the control law. And I think you could still use it for metering as well. I don't see any reason why you couldn't in terms of circuitry.
Okay. Then next up, Paul Colvin's possibly not a question, but he's raised an interesting part, the AFEX 1537, and included a link to the datasheet for it, which looks like a very interesting device. I can pass it on to various people, but yeah.
Ben Duncan talked about the AFEX device, and it was used in some automatic, if I remember correctly, it was actually used in some, if you like, VCA controlled mixing desks, automated mixing desks as the main fader. I think broadly that comes in, although it's done slightly differently and it has a slightly different control law, it's still a form of transconductance voltage controlled amplifier when you look at it. But yes, thank you.
Great.
I think.
Thanks to Paul for that. And final question from Andrew S. What are some of the resources, books or papers perhaps you would recommend on the topic?
I pulled things out from lots of different sources for the modern transistor-based VCAs. Ben Duncan's set of articles in Studio Sound was quite a good starting point, and that's available. There's a site called Radio History Museum, I think it's called, or the Radio History Museum, and that's a very useful resource. The Dolby things I got from looking up Dolby manuals, I have to say. and things like the variable mu and the LA2 and the FET one, basically I found via Google chasing up, I tend to say, you know, put in the name of the compressor and ask for the schematic and see who's got one. And you get a variety. Some of them you think that doesn't look like it's going to work. You have to use some element of judgment. And I wasn't showing the whole circuits. I mean, you can get the whole circuits, but certainly in the 60s and 70s, they weren't very logical about how, well, I'm sure it made sense in terms of building it, but it's quite hard to unpick the circuit because wires are sort of going thither and yon, especially with a feedback compressor. You've basically got wires coming from the back to the front. So you tend to have quite messy circuit diagrams. I don't really see much better than that. So for that bit, Google is your friend there. There are people have posted things up for the more modern implementations, you know, by companies, say Manley, who do an optical one. I think they tend to hold their circuits quite close to their chests because it's part of their IP, and you know you can't really fault them that. I did actually briefly get sight of an Analogue circuit. Unfortunately, I couldn't find it again, so that was my bad. But there are circuits out there that you can look at and experiment with.
Yeah, and just to add further information, certainly for the integrated circuits, THAT website has some good data sheets,
Yes.
notes. Sound Semiconductor has some good parts with descriptions.
Which one?
Sound Semiconductor.
Oh, Sound Semiconductor, yes. And I think if you check out the AES journal, THAT Semiconductors may have actually talked about their VC. They've certainly talked about some of their other products as AES papers, and I have a feeling their VCA was published as a conference paper at some point as well. So they are there.
Yes,
you can pick up stuff that way.
That's actually a good point. And I've, in preparation for this talk, went into the AES journal archive available to all AES members, and there are a lot of papers over the years, over the decades that your talk covered, describing all these types of technologies, papers from Gary Hebert from THAT and so on, describing this. So people like Andrew and others, please join the AES. You get access to all this information. It's there to just go and read. It's an amazing resource.
Yes. So
okay, so that was the last question. So I think it just remains for me to say thank you on behalf of everybody. We're getting lots of thank yous in the chat. Thank you very much to Jamie. This was an amazing talk. Certainly a talk that captured my interest immensely from the music synthesizer world. Thank you to the AES for hosting this, and thank you to everybody who came along and asked interesting questions.
Yes, thank you. Yes, I think I'd let me know if you'd like more talk about old circuits like that.
I think the answer would, yes, please.
Yes. Okay.
Definitely. What I just to add, there have been some questions about the video for this, so it will be going on the AES UK section website. Links to useful information we can also add to the YouTube page for that video. So we'll try to sort of follow up with some of those questions. So thank you very much, Jamie. Thank you, everybody.
Yeah.
And there we are, 8:15, time for dinner.
Time for dinner
Thank
and a
you.
drink or something, right?
Definitely.
Now, this is where we need to go to the pub. But never mind.
Thank you very much, everyone, and good evening, good morning, good afternoon,
evening.
wherever you are.
Yeah, cheerio.